Hello and thank you for watching my video. This one is on number theory from the multiplication table. Let's start with this 7 by 7 multiplication table, which is upside down compared to the way it's normally taught or written. And let's choose an n. Let's choose n equals 6 as an example, but as we go through we talk about what's happening with 6. We're really talking about what's happening generally with any n. Rather than filling out the whole table, let's fill in the numbers that are just 6 or less. And we don't even have to do multiplication. We can just go up each column or across each row, whichever way you want to do it. So for the first column, we're just counting up to 6. And for the rest, we'll be counting up in arithmetic progressions, starting with the number at the bottom, which is also the period. So 2, 4, 6, and then 3, 6, and then 4. But then 8 is greater than 6, so we don't fill that in. And it's the same for 5. No 6 will appear in these columns, the fourth and fifth column, because 6 is not divisible evenly by 4 or 5, but certainly by 6 itself, so we have a 6 appearing in the sixth column. Let's put a dot in the upper right corner of each little unit area square in which the number 6 appears on this table. The reason for writing the table upside down is that we can now, on the left edge and the lower edge, draw in Cartesian coordinate axes so that our table corresponds to the upper right quadrant of the Euclidean plane. And this then gives us the multiplication table as a labeled lattice in this upper right quadrant. And we can draw in our tick marks, and we wouldn't even necessarily need the labels now. We could use the tick marks and the lines along the tick marks to do our calculations. And we can see that these points in the upper right corner correspond to the products of whatever is on the x and y tick marks. And now we can draw a function, a step function, which is basically the numbers appearing on this table that do not exceed 6. So this red line is a function which we can think of as a curve, and then we can compute the area under the curve just by adding up the unit width columns. Each one is, of course, 6 divided by the number of the column. But when we get to 4 and 5, then we need to use the floor function because we don't want that fractional part. We're just looking at the integer areas. So the heights are the areas, and we get 6, 3, 2, 1, 1, 1, which total up to an area of 14 for the area under the curve. Let's call that area AN. Because the output of the floor function is the same as the argument when the argument is an integer, we can actually use the floor function across the board here without any ill effect. So we can write this formula as a of n is equal to the sum from x equals 1 to n of the floor function of n over x. And of course, if we want to, we can split that summation into two summations, one over the x values that divide n and the x values that do not divide n. Splitting it this way, the left summation has just the x that are divisors of n, and the right summation has the x that are non-divisors of n. So essentially, in our example, 6 appears 4 times because there are 4 divisors of 6. And it can be said generally that the number of times any given number appears in the multiplication table is the number of divisors of that number, which is the tau function. So tau of n equals 4 in the case of n equals 6. And because the x that divide n evenly, the divisors, there's no fractional part, and we can factor out the n and put it in front of the summation sign. So we can rewrite n in another way where we just go with the full range, x equals 1 to n over 1 to the x with that n out front. And now we subtract the fractional parts, the parts that the floor function would normally eliminate. But we no longer have the floor function. We have these curly brackets, which are basically the fractional part. So every fractional part, when you see these curly braces, that number is less than 1. And of course, the summation on the left is just the nth harmonic number. So we can rewrite a to the n as being n times h of n minus the summation of all the fractional parts. Let's take a closer look at the formula for the area based on using the floor function to determine the height of each column that we had before. Using the fact that the number of times a given number appears in the multiplication table is exactly the number of divisors of that number, we can account for this area in a different way by counting the tau function of each number for 6 or less. So we can write out the divisors of each of these numbers, and we then account for all of the unit square areas under the red curve, where the number of divisors of 1 is just 1. So the tau function can also be stated as the number of ways that a number n can be written as a product of 2 and only 2 integers, with 1 being an exception to that by definition. So we can just count the number of entries in each column above, and we get for these tau values 4, 2, 3, 2, 2, 1, which is a different distribution than what we had before using the floor function formula, but still we're adding up to 14 because these are equivalent. Recall with the floor function sum that we had 6, 3, 2, 1, 1, 1. This proves our first little identity, that the sum from x equals 1 to n of the floor of n over x is equal to the sum from x equals 1 to n of tau of x. Let's take this equation and add the fractional parts to each side so that we end up with the following here. So the left-hand side now is all of the integral parts plus all of the fractional parts, aka, as we saw before, n times the nth harmonic number. And so we can rewrite this expression here by subtracting the tau x sum on the left and leaving on the right-hand side the sum of the fractional parts. So that gives us a little expression for the sum of the fractional parts in terms of the harmonic number and this summation of tau of x for x equals 1 to n. Let's see how this works out in the case of n equals 6. Here I messed up a little bit writing this out, but essentially we're only going to have a fractional part for x equals 4 and x equals 5. And the long and short of it is that those are 1/2 and 1/5, and those sum up to 7/10. So our area with the fractions included is 14 and 7/10. And that then should equal 6 times the 6th harmonic number. Let's check it out. The 6th harmonic number is, of course, just the sum of 1 over x for x from 1 to 6, which, sparing you the gory details, is equal to 147 over 60. So if we multiply that by 6, we end up with 147 over 10, which is, of course, 14.7, which is, of course, equivalent to 14 plus 7/10. So that's it. In this construction, this labeled lattice, the labels themselves are really just the value of the point in the upper right corner of the unit area to the left and below the point. So there are obviously points for the rationals or even reals if you want. And in the case of 6 divided by 4, that extra 1/2 fractional part is going to be exactly halfway up the unit area. But that point on the upper corner, that still has a value of 6. If we were to write out the labels for the rational numbers, we'd put a 6 in that box, which is half hidden, if you will. But the same thing for 5. We're divided into 5 segments, and our fraction is 1/5. So we just need that bottom 1/5 high segment, in the corner point right there at 1/5 above 5 will be equal to 6 as well. With the fractional parts drawn in, we can trace out another curve like we did before, only this time it's going to be only coinciding with the original red curve when x is a divisor, and then it'll be riding on top of the fractional areas. So we get, and that is of course the curve n times h of n, and just sits slightly higher than the original curve. With this orange step curve, we have a upper corner point equal to 6 for every x column, along up every x column. And so just by extension we can imagine we have an x times y equals 6 point for every x value. So we can sort of draw them in, because this curve is basically x times y equals n. And so we can draw those in, and then we can basically eyeball and draw in the real curve x times y equals n along all those points. So we end up with a curve where x times y is constant and equal to n, or equal to 6 in this case. And of course we have this 45-degree angle mirror axis, so that everything on their mirror images on either side of each other like that. And that's a symmetry we wanted to take advantage of. In other words, if we were to swap x and y, these orange boxes of fractional areas, we would be writing them in this way on this side of things. But we're going to keep it like it is right now for the moment. And of course, the nature of that diagonal line is such that it is a collection of all points where x equals y. So it's squares. And it's interesting that despite all this symmetry, we have different fractional areas on either side of it. That is not symmetrical unless you swap x and y, then you get that symmetry. In this case, we have 0 fractional areas less than the square root of 6, because all numbers less than the square root of 6 divide 6. Same is true for 12. 12 is the last number where that works. After that, there's always a number less than the square root that does not divide the number. To better see how this works, let's look at n equals 7. Actually, we'll pick up from here in the next video in this series. Meanwhile, thank you very much, and God bless you.